Hello students, welcome back. Previously we discussed up to 1.2. Now using all those arithmetic properties, especially these, and now let us assume identity inverse, all those uniqueness and well-definedness, all those are now taken care of. And then let's go ahead with some properties of zero. How about these? Addition by zero doesn't change anything. There's nothing to prove here because that's the definition. Multiplication by zero, oh, that's nice. Any real number times zero is zero, and that's not one of those basic properties. So let's prove that. And then zero product property, x times y is zero, then either x is zero or y is zero. Okay. And zero division property, I think this one is trivial. Okay, alright, let's start with this. So x times 0 is, let's write like this. And that's because of what property? 0 is the additive identity. That's why this thing holds. Okay, and then what we do next? Too much space. I don't need that much. And then that's because the distributive law or the distributive property, whatever you may want to call, okay, and then if I subtract one of those away, then I'll be done, right? So x times 0 minus x times 0. What do you mean by minus? That means adding the additive inverse of that. Those are there before, and then subtracting added the same thing to both sides of the equality, and in that case the equality is going to be preserved because the addition is well defined. Remember that? Okay, all right. Left hand side is clear because I added the additive inverse, so left hand side is 0. Right hand side, I may have to do a bit further work. What did I just use? I used the associative law. Do you see that? Here, that was there before, and I just added something, so parenthesis there, and then added the additive inverse of x times 0. And then, of course, I can regroup. That's what the associative law is all about. And then remember, adding the additive inverse, I'm going to get 0, right? The additive inverse property just applied here. Okay, all right. One more and I'm gonna be done. Zero is the additive identity, so adding 0 doesn't change anything, so I can remove it from the right hand side. And then in the end, I got the desired conclusion. X times 0 is equal to 0. This is really thorough proof. Can you see that? I took every single step based upon some property of those, some arithmetic property here. And then not only that, on the right hand side, I gave all those reasoning. Here you see, in many cases, people skip these reasons because they are obvious. You know the reason, but they're obvious, so skipping. That's one thing. You're unsure about that, so you just skip it. That's very different. All right? You should know, and whenever asked, you should be able to answer why this equality worked out. So this part, which I just de-emphasize in gray, you can often skip. Yeah, most people skip when they're taking exams, but during the presentation or something, you may ask that kind of question to make sure whether your student know what they're doing. A bit too much space there. Okay, all right, that look better. And by the way, in this notebook, there is a simplified version. So starting from 0, work out, work out, work out, and then I wanted to get x times 0. So working backward. So how do you do that? X times 0 minus x times 0, that is adding the additive inverse. And then here 0 plus 0, and then use distributivity. And then associativity. And that's 0. So we end up with x times 0. It's a bit shorter version, but the idea is the same. This one, a bit longer version, perhaps a bit better version. And by the way, we just proved something times 0 is 0 when that something belongs to the real number. And as a matter of fact, it doesn't have to be a real number as long as we have some element from an algebraic structure that follows this property, and so something times 0 is 0. So for example, even when x is a complex number, this will work out. Even x is a matrix multiplication, yeah, that too will work out. Yeah, for matrix multiplication, for instance, we don't always have inverse matrices, but in the proof of this, we didn't use the multiplicative inverse property, so it can work out as well. But then again, can you think of something so non-algebraic that these kind of properties do not apply among the objects or some extended system that we had been dealing with? Well, one such example is this. 0 times infinity is not always 0 in 0 in general. Not always 0 in general. In Calculus 1 level, whenever you encounter 0 times infinity type limit, maybe not whenever, there are some exceptions, but most of those exceptions are really artificial, and 0 times infinity type limit usually turned out to be 0, but infinity doesn't follow any of those algebraic rule. It's not coming from any of those algebraic structure. Infinity is analytic object, not algebraic object. So this kind of thing doesn't apply. Can you think of an example that 0 times infinity type limit is non-zero? I mean, you can always create an artificial example like this. X squared minus 4 over x minus 2, and then rewrite this thing as the limit 1 over x minus 2 times x squared minus 4, like that, and then claim it as, oh, this is infinity times 0, and then this is some quantity, some finite quantity, which is going to be easy. Let's see. I think you're going to get 4. Anyway, this is cheating. This is 0 over 0 type limit artificially turned into 0 times infinity type limit. And many of the trick problems are like that too, because all those trick functions have reciprocal trick. So that's cheating. I'm talking about something essentially 0 times infinity generating something else. Think about that example. It's going to be difficult to find an example from Calculus 1. Probably you'll have to go to Calculus 2 for that. Wait, not everybody here in this class has required Calculus 2, I think. Okay, okay. If you're in middle school teacher track, and if you're not taking Calculus 2, then please forget about this comment, and you don't really have to think too much upon. But if you're going over to high school teacher track, then think about that. What example can you find? Okay, next, zero product property. So, well, I'll leave the proof to you. It's going to be simple. But let me tell you the implication of this. For example, if you solve a quadratic equation, all right, s squared minus 4s plus 3 equal to 0. All right, how do you solve this? S minus 3 times s minus 1 equal to 0. You take the factorization, remember that? It's an easy factorization because this is monic trinomial. And then, what follows? Yeah, s minus 3 is equal to 0, or s minus 1 is equal to 0, and therefore s is 3, or you get this conclusion, all right? And it's essential that we have zero product property. From here to there, we need zero product property. So if you have an algebraic structure that does not satisfy the 0 point property, zero product property, then solving a quadratic equation there can be a heck of a lot more tricky. Can you think about that kind of example? And then zero division, oh, I'll leave those details to you. Let's see, how about properties of 1? I'll leave those to you. Properties of signs. Okay, we'll discuss this in the next video. Properties of rational numbers. Okay, we'll discuss that in the next video as well. Okay, so far so good. See you in the third video.